So let's look at the moment generating function of a Gaussian distribution. And this is the definition of the moment generating function for the random variable capital X. And it's a function of this parameter t. And for more information about moment generating functions, check out the link in the description below the video where there's the definition of moment generating functions. But here we've got this expectation, and this is the definition. So let's write this out for the Gaussian. So what this means is the expectation means the integral over the value. So it's an integral from negative infinity to infinity over the value, which is e to the tx, multiplied by the PDF for the random variable. And the random variable is x. So here we've got the PDF for the Gaussian is, of course, 1 divided by 2 pi sigma exponential of minus x minus mu, which is the mean, squared, divided by 2 sigma squared dx. So this is the probability of getting that value x. So it's the expectation. Again, there's a link below the video for an explanation of expectation, but it's the value multiplied by the probability of getting that value, which is the PDF multiplied by dx. And again, you can see the description for that in the video in the link below. So here we have this expression here, and now we just really need to manipulate this expression. And it can look difficult and complicated because it's an exponential of a squared value of x, which is difficult to evaluate. But let's see how we can manipulate that. Well, here I've just rewritten the expression here. I've collected the exponential terms, and I've therefore taken the tx inside the exponential parameter, and I've pulled out the 1 on 2 pi sigma out the front. That's all I've done there. Okay, and now I'm going to look at the term inside the exponential here, and I'm going to collect all of the x squareds and all of the x terms. So here we are here. I'm just simply looking at this expression in here. We've got the minus x squared, and then we've got the minus with the minus. So we've got 2 mu x, and we've got the tx here. But of course, the tx needs to be put on the top of 2 sigma squared. So we've got 2 sigma squared times t times x. So we've just collected the x terms. So now we have an x squared term, an x term, and another term, which doesn't depend on x. So we can complete the square here. And so let's do that. So here we've got simply, you can see, completing the square, we need to have, this has got the 2's already. So we need to have mu plus sigma squared t. That's the mu plus the sigma squared t from here. And so if we've got x minus mu plus sigma squared t in here, then we will be getting because we've taken the negative out the front, then we'll be getting exactly this expression here with an extra term left over, which is 2 sigma squared t times mu, because this is this term here that's left over. Once you square this term here, you'll be left with some negative terms that don't depend on x, and these are what those extra ones are that cancel them out to give you this expression. I think hopefully you can see that directly. It's simply by completing the square and writing out what's left. Okay, and so now we have this term here, and this is a squared term here of x. And let's put it back into this exponential here. So we do that by putting this term here into the exponential. And of course, this also has to go into the exponential, but now we separate it out because this term does not depend on x. So again, it goes into here, we divide by the 2 sigma squared. So this just becomes t mu, and this one becomes a half sigma squared t squared. And that's now when we separate it out of the exponential, because we can have 2 terms for the exponential here, this term plus this term. This term does not depend on x, it can come out of the integral. So here it is here outside the integral. And now we're left with an integral with this term here where there's the x minus something squared. And this term here, how do you evaluate this integral? Well, we can observe directly this integral is in exactly the form of a Gaussian. So it's a Gaussian with a variance of sigma squared and a mean in this case of mu plus sigma squared t. It's just got a different mean. But we're integrating from negative infinity to infinity, so we know because it's a Gaussian, we know that the area under the Gaussian equals 1. So this entire integral here with the 1 on 2 pi sigma, the entire integral here simply equals 1, and we're just left with this term here. So this is the moment generating function of a Gaussian. So hopefully this derivation has helped you to understand how it comes about, how this is derived. If it has, please give the video a thumbs up. It helps others to find the video. Check out the web link in the description below where you'll find a fully categorized listing of all the videos on the channel. And don't forget, subscribe to the channel for more videos.